Hi guys, welcome to this video where I'm going over the semester 1 practice final. Do note the format for the final. There are going to be this amount of questions for every single chapter, and the emphasis is mostly going to be on the chapters on trigonometry, so chapters 4 and 5. And in this study guide, you'll encounter all the questions that will potentially appear in the final, and there's a very close correspondence there, and the difficulty of the final will be slightly easier than the study guide as usual. Start with question 1, exponents and logarithms here. So question 1 has us trying to solve for x given this exponential equation, and the goal for these kinds of questions is always to get both sides under the same base, so the same exponential base. And then once we're able to get them both under the same base, we're able to set their exponents equal to each other and then solve for whatever variable we have. So in this case, clearly, we are going to probably try to solve for x by making both sides base 7 exponents, right? So the right side is clearly square root of 7 is just 7 to the power of 1/2. So we can write the right side as 7 to the power of 1/2. And the left side is a little more tricky because we have a kind of nested exponents here. First, 1 over 49, that is 7 to the power of -2, right? Because 49 is 7 squared, and then we have a reciprocal of 49, so that's a -2 exponent. And so we're able to write this 7 to the -2 power within the parentheses, and then -2x plus 1 as an additional exponent. And of course, when exponents stack on top of each other, we know that they multiply, and so the left side is also equal to 7 to the power of -2 times 2x plus 1. Sorry, -2x. -2 times -2x plus 1 in parentheses, because those exponents multiply. And so now that we have the exponents under the same base, we're able to set their powers equal to each other. And so we have -2 times -2x plus 1 equals 1/2. All right, so that's just a simple equation that we can solve. The left side expands as 4x minus 2 equals 1/2. And so that means 4x equals 5 over 2, which means that x equals 5/8. Next question, we're able to simply directly set the exponents equal to each other because their bases are already the same. They're both base e exponents. And so we're able to simply write 2x squared plus 7x equals -3. And so that means we just have a quadratic in terms of x if we move this 3 to the left side. And so because we have a quadratic equal to 0, all we need to do is factor the left-hand side, and we'll be able to get x. Okay, so the left-hand side factors, right, if we factor by grouping, we just multiply a times c, that gives us 6, and we're looking for two numbers that multiply to 6 but add to 7, the term in the middle. And then so we're going to split that 7 into those two numbers. Those two numbers are going to be 6 and 1, and so the left side becomes 2x squared plus 6x plus 1x plus 3 equals 0. And then we factor by grouping. So the first two terms factor as 2x times x plus 3, and the second two terms factor as a 1 times x plus 3. And then we factor once again by taking out that x plus 3 term. So this becomes 2x plus 1 times x plus 3 equals 0. And so our answers are going to be x equals -1/2 and -3. Okay, no extraneous solutions here because we have an exponential function which takes all values of x, so there are no issues with negative numbers. All right, number 3 is a very tricky logarithm question. We have a strange logarithm in the base, or strange numbers in the base and also strange numbers in the input. Oh, there's some ambiguity here. There should be another parentheses around this, actually. Okay, so the way to do this question is by doing a change of base. Okay, so if you guys recall our change of base formula, right? That is log base A of B, or I think my formula was B of C. Log base B of C is equal to log base A of C over log base A of B. Okay, so we're allowed to change to any base that we like. So A is any number, or actually I believe any number other than 0 or 1, any positive number other than 0 or 1, but essentially any number. And the C is going to go into the numerator, and the B, the base, right? Think base below, base goes to the bottom. Okay? And so we're going to choose a suitable base to change to, and clearly the best base here is base 2, right? Because these are both numbers that are powers of 2. So we're going to change to base 2, which means that this is equal to log base 2 of 1/8 to the 3/4 over log base 2 of root 2. Okay? So we might want to rewrite this a little bit so that they're powers of 2, actually. If you did that, you would find that the top is equal to 2 to the power of -9/4. Okay, why is that? That's because 1/8 to the 3/4 equals 2 to the power of -3 to the 3/4, right? Because 1/8 is 2 to the -3, and so -3 times 3/4 is -9/4. That's how we got 9/4 there. And then the bottom is just equal to log base 2 of 2 to the power of half, because the square root is a power of 1/2. Okay, so these simplify. The logarithms cancel with those exponent bases, and so we're left with -9/4 over 1/2. Okay, so that's just -9/4 times 2, which is equal to -9/2 as our answer. Let me just check my work here. Looks correct. Okay, next question has us using some properties of logarithms. So logarithm arithmetic. So here we're going to use the property that whenever we add logarithms, their inputs multiply, and then whenever we subtract logarithms, their inputs divide. Okay, so log of b plus log c equals log bc. Okay, any base, as long as they're the same base, so they have to be the same base. And then log base a of b minus log base a of c is equal to log base a of b over c. Okay, and so we're going to use those properties here. We can probably just start with the first two logarithms. That's going to give us log base 3 of 96 divided by 8, which is 12. Okay, so the first two logarithms subtracted becomes log base 3 of 12, and then we still have that 4 there. And then when we do this again, this subtraction becomes log base 3 of 12 over 4, which is log base 3 of 3. And so log base 3 of 3 is of course just 1, because 3 to the power of 1 is 3. So that's our answer. All right. Alternatively, you could have also grouped the latter two terms as such. So you could have made the latter two terms an addition and done it like that. So this is just another way of doing it. So when those terms are added, that's log base 3 of 32. And when you divide it again, that's log base 3, because 96 divided by 32 is 3. Okay, so another way of doing it. Let's do some of the graphing questions. So we have this question asking us to find the horizontal asymptote and the y-intercept of an exponential function, right? So some very simple rules. First, we're going to find the horizontal asymptote. So that is actually very simple, because the horizontal asymptote of an exponential function is always going to be whatever constant we're adding or subtracting at the end. Okay, the reason for that is because the basic exponential function, so anything, e to the x, 2 to the x, 3 to the x, that's always going to have a horizontal asymptote of y equals 0, so the x-axis. And so whatever constant we're subtracting or adding to the end, that's going to perform a vertical shift, either upwards or downwards, and shift that horizontal asymptote to some either higher value of y or lower value of y. And so all we need to do is just look at that number right there and write y equals that, okay? So the horizontal asymptote here is y equals -1. Okay, it's very important to have this y equals, otherwise it doesn't make sense. The horizontal asymptote is not a number, it's a line. And so you need to have that y equals there in order to get the credit. Y-intercept, that is not hard to find either. Remember, y-intercept is wherever the graph crosses the y-axis, and so that's wherever the graph has an x equal to 0. And so to find the y-intercept, you just plug in x equals 0 into the function. All right, so we're going to plug in x equals 0. So for the y-intercept, f of 0 is equal to -2 to the 1, right, -1, because that's when x equals 0. And so this is just -3. So our y-intercept is 0, -3. Okay, so this is almost the amount of information we need to graph. The only thing we now need is to have some information about what kind of transformations have occurred to make this function into what it is now. Okay, and in particular for graphing, what we really need to know right now is simply the reflections that have occurred. Okay, all the information about the shifts are encoded into this horizontal asymptote, or this y-intercept. And all of what remains is simply for us to know the shifts, the reflections that have happened. And so in order to determine what kind of reflections are happened, we're going to look at two things, okay? For the horizontal reflection, we're going to ask ourselves whether x has been negated or not. In this case, yes, x has been negated because there's a minus sign right in front of the x. And so that tells us that a horizontal reflection has happened, okay? So has there been a horizontal reflection? Yes, okay, because there's a minus sign in front of the x. Has there been a vertical reflection? The answer is also yes, because there is a minus sign in front of the entire exponent, okay? That's all you need to look for in order to determine whether a horizontal reflection has happened or a vertical reflection has happened. There is a vertical reflection because there's a minus sign right there in front of the base of the exponent. All right, and so now we are ready to graph. Okay, so we're going to draw our axes. Doesn't need to be fancy. Don't need any tick marks. Just an x and y label is sufficient. And then we're going to draw our horizontal asymptote. So that's at y equals -1. Put that in red. So that's at -1. And then our y-intercept is at 0, -3. So we'll put that right here. Okay, 0, -3. All right, and so has there been a vertical reflection? Yes. Has there been a horizontal reflection? Yes. Okay, so what would our original graph had looked like in terms of its shape? Right, the graph of 2 to the x would have looked something like this. Right, it would start flat and then increase upwards exponentially when it goes to the positive direction. But now we know that both the horizontal and vertical shift has been applied. Sorry, horizontal and vertical reflection has been applied. And so that means we know that actually the graph must go like this. Okay, it should start close to the asymptote in the positive direction, but now it's going to decrease exponentially when it goes in the negative direction. Okay, and that's because of both reflections that have been applied. To do the next one, which is very similar principles, just now we're doing a logarithmic graph, right? So if you recall, right, the exponential graph looks like this. So this is e to the x. So the exponential graph always has a horizontal asymptote, but the logarithmic graph has a vertical asymptote, and it'll look like that, right? This would be a log graph. If you notice, they're inverses of each other, so they're reflections across the y equals x line. But it's important to know the basic shape of the graph so that you know how to transform them into the eventual form that you're asked to graph. So let's start with finding the domain, x-intercept, and vertical asymptote. All right, so domain is very easy. All we need to do is set the input to be greater than 0, right? Because for logarithms, that's the only rule for logarithms. The input of the logarithm has to be greater than 0, so that's what restricts the domain. All right, so the domain is whenever 1 minus x is greater than 0. And if we rearrange that, we would get x is less than 1 as our domain. X-intercept is a little tricky sometimes, because what is an x-intercept, right? An x-intercept is whenever our graph hits the x-axis, which means that it's whenever our graph has a y value of 0. So we're asking ourselves which x value will give us an output or y value of 0. So we actually have to solve an equation. In this case, we have to solve this equation ln of 1 minus x equals 0. And the way to solve this, of course, logarithm only equals 0 when the input equals 1, okay, because ln 1 is 0. Alternatively, you could also, exponentiate both sides, base e. So the left side becomes e to the ln 1 minus x, and the right side is e to the 0. And we do this because this would cancel out the logarithm, right? So the left side would become 1 minus x, and the right side becomes e to the 0, which is 1. And so that just gives us x equals 0. So that means the x-intercept is 0, 0. Right? X value of 0 and y value of 0, because it's on the x-axis. Vertical asymptote is very easy and similar to the domain. The asymptote always occurs whenever the input equals 0, right? Because it can never equal 0, but it can get really close to 0. And so we solve for the asymptote by just setting 1 minus x equal to 0, which tells us that x equals 1. Okay? You can also always just write the asymptote just by converting this inequality into an equality. All right, so now we can graph it. So we're going to start by graphing the asymptote, I guess. So that's a vertical 1. Vertical asymptote going through x equals 1. So we'll put that here. Now we're going to sketch the intercept, which is at the origin. The origin 0, 0. And so then we're going to think about what the shape of the graph is like, okay? So we first think about what the graph would have looked like without any transformations, right? And that's always like this. The graph would have looked like this. So a vertical asymptote, and then it kind of increases like that in the positive direction. But, have there been any reflections that have happened? Has there been a horizontal reflection? Answer is yes, because we have a minus sign in front of the x. Has there been a vertical reflection? Answer is no, because there is no minus sign in front of the logarithm. Okay, so same principles as for exponential functions. And so we know that from our original function, there has to be a horizontal reflection, but there's no vertical reflection. And so that means our final graph looks like this. Okay, so we start always at the asymptote, and then we just increase kind of in that exponential direction. Your graph does need to be facing the right direction, and it also needs to start super close to the asymptote. Right? It's not an asymptote if you're just going to start, a whole unit away from it. Let's do the next question. Condense this expression to the logarithm of a single quantity. So we're going to use our rules for logarithms here. In addition to the previous addition and subtraction rules, another important rule here is the rule for multiples of logarithms. So whenever we have b times log base a of c, this is also equal to log base a of c to the power of b. Right? So multiples of logarithms, that always corresponds to some kind of power of the input. And so that means using this principle, we can apply that to the logarithms we have here. And so this would become ln of xy to the power of 4. All right, we just move that constant to become an exponent here, minus ln of z squared to the power of 5, right? Or that's also z to the power of 10. And so now we have two logarithms being subtracted, so we know that we can just divide the inputs. And so this becomes ln of xy to the power of 4 divided by z to the power of 10. Okay. You could also rewrite this as ln of x to the 4th, y to the 4th, right? Because the exponent distributes over the multiplication over z to the power of 10. Let's do the next one, a logarithmic equation. Here, we're going to use some properties of logarithms. The first one is that when we add logarithms, their inputs multiply. And so this left-hand side becomes log base 5 of x times x plus 3, because we're adding two logarithms. And the right side is just log 5 of x plus 24. Okay. Well, now, if we have two logarithms with the same base equal to each other, then their inputs must also be equal to each other. That's the one-to-one property, right? So that means we can set the inputs equal to each other, and now all that remains is for us to solve this quadratic. So the left side expands like that, which means we can rearrange the terms. We're left with that, which factors. Okay, so, right, we might be tempted to box the answer now, but whenever we have logarithmic equations.
This is the high school 5-minute warning bell. Please head to class.
Whenever we have logarithmic equations, we always need to remember to check for extraneous solutions, right? Because logarithms do not have an infinite domain. And so in this case, x equals -6 is not, x equals -6 is not a valid solution because it causes both these logarithms to have negative input values. So we're going to cross out -6, and we're left with just x equals 4. Next one. All right, here we have a quadratic in terms of e to the x. To make this more clear for you, you can set y equal to e to the x, which means that e to the 2x is simply y squared, right? So this becomes y squared minus 2y minus 15 equals 0. Or y minus 5 times y plus 3 equals 0. All right, so that tells us that y either equals negative 3 or positive 5. In other words, e to the x either equals negative 3 or positive 5. All right, so we can just take a logarithm of both sides, and that tells us that x equals ln of 5. All right, negative 3 is impossible because e to the x can never equal negative 3, right? Exponents always give us positive numbers. You could also see that, right, if we took a logarithm of both sides, we would have had ln of negative 3, but that's impossible because logarithms can't have negative inputs. Okay. Let's move on to the trig. Chapter 4, let's evaluate the following. These are easy unit circle questions, right? We should know them by now. So 11 pi over 6, that is 2 pi minus pi over 6. So that's going to be right here on the unit circle. And so that sign value is just negative half. 5 pi over 4, right? That's pi plus pi over 4. So we know that's right here. And so that cosine value is an x value, so that's negative root 2 over 2. And then 5 pi over 3, that is 2 pi minus pi over 3. So it's going to be right here. And so that tangent value, right, sine over cosine, and the sine is negative root 3 over 2. And the cosine is 1/2. So that gives us negative root 3 as our tangent. Okay. So following these 3 easy unit circle questions, you are going to get 2 more hard unit circle questions, and they are challenging because these angles are either greater than 2 pi or much less than 0. And so in order to convert it into a more helpful angle value, we have to subtract some multiple of 2 pi. Okay? And the reason is because whenever we subtract any multiple of 2 pi, we're always going to return to the same point on the unit circle, because all these functions have a period of 2 pi, or pi, which is still okay, because that's a fraction of 2 pi. Okay, so to solve these questions, we're going to subtract some multiple of 2 pi or add some multiple of 2 pi until we get an angle that's between 0 and 2 pi. It has to be 2 pi, okay? So you can only subtract 2 pi or 4 pi or 6 pi, right? You can't subtract pi or 3 pi or 5 pi. Those will not give you the right answer for sine, cosine, secant, and cosecant at least. All right, so for 25 pi over 6, we're going to subtract 4 pi. So that is 24 pi over 6, right? And so that's just going to give us pi over 6. So really this is equal to cosecant of pi over 6. Which is 1 over sine pi over 6, right? And that is just positive 2, because sine pi over 6 is half. Okay, next question is very similar. We're going to try and add a multiple of 2 pi. In this case, let's think. We'll add 12 pi. Okay, might take some trial and error to get the right value or right multiple of 2 pi. But in this case, we're going to do 12 pi, or 36 pi over 3. And that is going to give us 5 pi over 3 as our equivalent angle. All right, so this is really asking us what is cotangent of 5 pi over 3. And that is just going to be cosine of 5 pi over 3 over sine 5 pi over 3, which is equal to 1/2 over negative root 3 over 2, which is equal to negative root 3 over 3, after we rationalize it, which is a must. Okay? If you don't rationalize, you'll lose points. Rationalize. All right, finding two values of theta such that tangent theta equals negative root 3. So we're just going to go to the unit circle. All right, the trick that I like is I know tangent corresponds always to a slope. And so that's just going to ask me which 2 points on the unit circle give me a slope of negative root 3. I know negative root 3 is steeper than negative 1, so it must be these 2 points here. So that tells me I have that point and that point, and so theta equals either 2 pi over 3 or 5 pi over 3. Okay? Alternatively, you could have thought about, which two values of sine and cosine would give you that value of theta. So we know that tangent is sine over cosine. And so we know that either it would have been positive root 3 over 2 over negative half, or negative root 3 over 2 over positive half, right? And so that's either 2 pi over 3 or 4 pi over 3 for those values of sine and cosine. Which quadrant of the unit circle is theta in? If secant theta is greater than 0 and cotangent is less than 0. So if secant is greater than 0, that tells us that cosine is greater than 0, right? Because secant and cosine are reciprocals of each other. So if cosine is greater than 0, that means we're looking at a positive x value, right? On the other hand, if cotangent is less than 0, that tells us that cosine over sine is less than 0, which means that x and y must have opposite signs, right? Opposite signs. Because cosine over sine can only give us a negative number if they have opposite signs, negative over positive or positive over negative. So that tells us that if x is greater than 0, as we know, that y must be less than 0. So that's going to correspond to quadrant 4 here. Moving on, let's look at a function that is represented by this graph. So the first step is always to think about the period. And then we're going to think about the minimum and maximums of this graph. So the period, all right, represented by t, the period is going to be pi. The reason because for period, we always look at the distance between the peaks, and that's just clearly pi. So the period is pi, which tells us that the b value, or the constant in front of the x, is going to be 2 pi over t, which is 2 pi over pi, which is 2, right? Next, our maximum, right, is at 6, and our minimum is at 0. So that tells us that our average is 3, and our amplitude is also 3. Okay? So amplitude is always the number that's multiplying the sine or the cosine, and the average is the number that's being added to the end. Now we're going to think about whether this is a sine graph or a negative sine graph or a cosine graph or a negative cosine graph, right? So you might want to jog your memory a little bit. Sine always goes through the origin with a positive slope. So that's sine. Negative sine is just the reflection of this. So that passes through the origin with a negative slope. Cosine always passes through the y-axis with a peak. So this is cosine. And then negative cosine always passes through the y-axis with a dip. Just a reflection, right? So looking at this graph, we can clearly see that it's a negative cosine graph because it has a dip at the y-axis. So we're able to write the final equation as -3, right? The amplitude. Amplitude is always multiplying the cosine or sine function. So -3 cosine of bx, so 2x, and then plus the average, plus 3. That's our answer. All right, you could have also solved this question using some horizontal shifts. In that case, you would not have a negative cosine graph. You could have done a sine graph that was shifted, or a negative sine graph shifted, but that's a little more tricky and it's not required. But it would have given you an equivalent answer. If you want to check that answer, you can just graph it using some online graphing calculator. All right, so on the test, you're going to have 2 questions on sine and cosine graphs. So here's our second one. All right, let's first think about, is it sine or negative sine or cosine or negative cosine? Here we clearly have a negative sine graph because we're passing through the y-axis with a negative slope. Not the origin, because it seems like we do have a vertical shift, but it does pass through the y-axis with a negative slope, so it's negative sine. Let's think about what the period is. Okay, that's actually pretty tricky. But the answer is that the period is 4 pi. Okay, why is it 4 pi? Well, there are different ways of looking at it. You can either first draw the average. So the average line is clearly at 2. And the period is always the amount of horizontal distance that is required to have 2 intersections with the average line. So we're looking at the distance between here and here, right? So that's 1 full period, right? This is only a half period, right? So the full period is the amount of time it takes for you to go from one positive crossing to another positive slope crossing. And that's clearly a distance of 4 pi. Alternatively, you could have looked at the distance between a dip and a peak. That's also half period, so that distance is 2 pi, so that would have given you a period of also 4 pi. Okay, so the period is 4 pi. which means that b, which is 2 pi over t, is equal to 1/2. All right, what's the maximum? 6, once again. The minimum here is -2, so that tells us that the average is 2, and the amplitude is 4. And this is a negative sine graph, right? And so our answer is going to be -4 sine of b times x, which is 1/2 x, or x over 2, plus our average, so plus 2. That's our answer. Once again, your answer also could have been a shifted version of some other trig function, but if in that case, it's still correct, but just check your answer using some graphing calculator. All right, you're also going to have one question, either on tangent or cotangent, or secant or cosecant. Okay, so a lot of different possibilities. If you want more practice recognizing those, I would go to one of the study guides for Unit 4, Chapter 4. Yeah, a lot of different graphing questions there. So I can take one look at this and I can recognize that this is a negative tangent graph. Okay. What is the difference between tangent and cotangent? Well, the basic rule is that tangent crosses the origin. Okay, assuming there are no shifts, it crosses the origin. Whereas cotangent has a vertical asymptote at the y-axis. Okay, so tangent has this shape naturally, whereas cotangent always has this shape without any shifts. Okay, cotangent looks like that. Has a vertical asymptote at the y-axis. Okay, and not only a vertical asymptote, but it also goes in the opposite direction than tangent, assuming there are no shifts. Okay, so those are the basic rules for tangent and cotangent without any shifts. So you might be tempted to just look at this graph and notice it goes in a downward direction and just write it off as a cotangent function, but you would be wrong because it crosses the origin. And so in order to be a cotangent function, it would have to have some shifts as well. But without any horizontal shifts, this is actually a negative tangent function. Okay, it's a vertical reflection of a tangent function, because the tangent function normally goes in this positive direction, but with a shift, it would cross the origin with a negative slope, which is exactly what we have here. Okay, so we know it's a negative tangent function, and the second order of business is just to determine the period, which would give us the value of b, right? So in this case, the period is clearly pi over 2. How do we know that? We know that it crosses the x-axis once every pi over 2, so that's going to be the period. So what is the value of b? What is the coefficient in front of the x? Well, remember, for tangent and cotangent, the formula is not 2 pi over t, but the formula is actually pi over t, because normally tangent and cotangent both have a period of pi and not 2 pi, and so the formula has a slight adjustment. I'll make sure to remember that. And so the equation here is pi over t, and so b equals pi over 2, which is pi times 2 over pi, which is 2. So the answer is negative tangent of 2x. All right, let's do some of these inverse trig functions. All right, so for inverse trig, remember the restricted domains, the restricted ranges of the arcsine, arccosine, and arctangent functions. Okay, so remember arcsine can only give you a value between negative pi over 2 and pi over 2. So on the unit circle, it's only going to give you stuff in this region. And when we're here, it's always a negative angle. It's not going to be like 5 pi over 3, rather it will be negative pi over 3. Okay, so the range is always negative pi over 2 to pi over 2. Arc cosine is a little different. Arc cosine, the range is restricted to 0 to pi, right? 0 all the way to pi. And then finally for arc tangent, the range is very similar to arcsine. It's just a little different because we're not actually going to include the endpoints, negative pi over 2 and pi over 2, because those have undefined tangent values. So we would use an open circle, and then that would be the range. Negative pi over 2 to pi over 2 non-inclusive. Okay, so keep that in mind whenever we have these inverse trig functions. Here we have an arcsine function, and we're asking ourselves which angle would give us a sine value of negative root 3 over 2. So on the unit circle, which angles give us a sine of negative root 3 over 2? That is clearly either this one or this one, right? Either 4 pi over 3 or 5 pi over 3. But, we have to be careful because we need to make sure they're in the range of our arcsine. And in this case, only this value is within the range of the arcsine function, right? And we not only need to remember that, but it also has to be between specifically negative pi over 2 and pi over 2. So we can't write this as 5 pi over 3, okay? That would be wrong. We have to write it as negative pi over 3. Okay, so that's the answer. Okay? Because it has to be between negative pi over 2 to pi over 2. So if you wrote 5 pi over 3, that would have been wrong. Instead, you need to subtract 2 pi and get this particular angle value. All right, so you need to subtract 2 pi, go 2 pi around backwards. It gives you negative pi over 3. Okay, here we have a composition of trig functions and inverse trig functions. To solve these, we need to think about, we always need to draw a triangle somehow, okay? So we're first going to do an intermediate step. All right, this is how we solved it. We solved it by writing theta equals arc cosine of x. So what does that tell us? That tells us that cosine theta equals x, right? And so if cosine theta equals x, we're able to draw a triangle. On a triangle, that tells us that if this was theta, then that means the adjacent would be x if the hypotenuse was 1. Okay, so because cosine is adjacent over hypotenuse. And so therefore, we have this triangle here, which means that the other side is going to be the square root of 1 minus x squared. That's by Pythagorean theorem, right? And so our question is finding cosecant of arc cosine of x. In other words, we're looking for cosecant of theta. And so what is cosecant of theta based on this triangle? Well, it's just going to be the hypotenuse over the opposite, right? Because it's 1 over sine. So the answer is 1 over square root 1 minus x squared. All right, for these questions, whenever we have x's, we don't need to rationalize.
This is the junior high 5-minute warning bell. Please head to class.
All right, let's do these 3 matrices questions, and then we'll take a quick break. Well, I will take a quick break. You should keep studying. Okay, we have a matrix multiplication question. So first, let's check the, dimensions of the matrices to make sure that they're compatible for multiplication. This is a 3 by 1, right? Remember, it's always row by column, RC. Row by column, 3 by 1. And this is a 1 by 3. So are those compatible? Answer is yes, because these dimensions in the middle, they match. What kind of dimension is it going to give us in the end? It's going to give us a 3 by 3 matrix, right? Because we just kind of delete these in the middle, and we're left with 3 by 3. Okay, that's the kind of general rule. So you can use my trick for doing these multiplications. Do the first matrix on the left side. So put the 3 minus 5, 2 here on the left. And then we write the second matrix on the top. So that's 2 minus 3 minus 4. Okay, and then to multiply these matrices, we are going to go element by element. So the value here is going to be 6. Now here we have -9, and then -12, etc.